Okay, so
yeah, so today we are happy to have Jarah Evslin from Institute of Modern Physics of Chinese Academy of Sciences from Lanzhou, officially still. He will talk about Schrödinger wave functionals. Thanks a lot, Jarah. You can start.
Oh, sure. Okay, so today, as you heard, I'd like to give an introduction to Schrödinger wave functionals. So this is a kind of analysis-heavy talk, and analysis has always been my weakness. So that's part of the motivation for the talk, is looking for as much help as I can on this starting project. Okay, so the basic idea behind the talk is the following. Quantization is any procedure which takes you from a classical theory and gives you a quantum theory. In general, it either doesn't exist or it isn't unique. But if it does exist, then it does the following thing. If you've got a classical configuration space C, then the quantum configuration space is going to be somehow inside of the space of maps from C to the complex numbers. And intuitively, there's a natural embedding from the classical configuration space into the quantum configuration space, which is just to every classical configuration, you associate a quantum configuration which has support on that classical configuration. So basically, the wave function is non-zero only on that one classical configuration. Now, today I'll talk about two different tools for studying quantum theories. The first one is the semi-classical expansion, and I'll argue that the semi-classical expansion only probes a tubular neighborhood of this embedding. And so the topology of the seen by the semi-classical expansion is the same, just a deformation retract of this topology of the classical theory. And so you won't find any new topology here in the semi-classical expansion. And I'll also argue for you that instantons are described by homotopies between two embeddings. And so instantons may be sensitive to the topology of this bigger space of maps. Okay, so it's just some intuition. So here's the outline of the talk. I'm going to talk about Schrödinger wave functionals. And Schrödinger wave functionals are going to be these maps over here. Schrödinger wave functionals in two different settings. The first one is quantum mechanics, where they're just maps from a finite-dimensional manifold to the complex numbers. And that'll be half of the talk. And the other half of the talk is going to be quantum field theory, where you have this classical configuration space. If it's a scalar quantum field theory, is a set of maps from a finite-dimensional manifold to another one. And Schrödinger wave functionals are maps from these maps to the complex numbers. So at each map, it associates a complex number. And notice the scalar quantum field theory reduces to quantum mechanics if you just take M to be a point, because then C is the same thing as N over here. And remember, the C was just the configuration space of the classical theory. Now, there are a lot of quantum field theories out here. These are scalar quantum field theories, but sometimes people are interested in other quantum field theories. So, for example, Yang-Mills theory, instead of considering maps, you'd consider principal bundles. Or QCD, instead of considering just principal bundles, you'd also add a principal bundle together with an associated vector bundle and a choices section. But they're all basically variations on the same thing. You take some complicated object and you consider maps from that to the complex numbers. Okay, so any questions before I start? Okay, so for each theory I'm going to talk about, I'm going to introduce 4 different objects. First of all, an algebra, A. Second of all, a vector space that the algebra acts on. And the Schrödinger wave functionals are going to be in one-to-one correspondence with elements of this vector space over here. Then I'll pick an element of the algebra, and I'll call it the Hamiltonian. And then I'll talk about a subspace of this space over here, which is spanned by the eigenvectors of the Hamiltonian with finite eigenvalues. So remember, this big space is in one-to-one correspondence with the Schrödinger wave functionals. So the basic problem here in this field is to ask which of these Schrödinger wave functionals correspond to the subspace. That's the basic question that you want to answer. Okay, so are there any questions about generalities, or I get on to quantum mechanics?
Maybe one short question, if you don't mind.
Sure. Yeah, please.
The module V, if you are talking about the self-adjoint operator in the A, so the module V is a Hilbert module, right? So that you have an idea what it means to be self-adjoint. So it's not just a vector space, but actually an inner product space or so.
Well, I'd like to say that it's an inner product space, but in practice, it's got a measure in it which doesn't really exist. So things are a little bit hard to define in V, which is why at the end I reduce it down to the subspace, because the subspace is much more manageable. So V is a kind of formal thing. I don't know if you could put a Hilbert space structure on it or not.
All right.
But then I go down to this manageable thing once I've defined the operator H.
because the star structure, this involutive structure of the algebra, should somehow intervene with the module, right?
Yeah, so you'd like to have a nice compatibility condition between the star structure and the module, and I think you can make that all precise in the subspace. But in this bigger space, I'm not going to need to do any inner products in the bigger space, so I'll try to leave that. Okay, any other questions about that? All right, so let me start with quantum mechanics. This is a more familiar case. So in particular, what's called one-dimensional quantum mechanics. So here your algebra's got three generators, phi, pi, and h bar. H bar is in the center, and phi and pi satisfy these canonical commutation relations. And h bar defines the grading. So this is a graded algebra. And sometimes we can forget the grading just by setting h bar equals to 1. Now let me just make a comment about my conventions. So this is what gets called Schrödinger picture in the literature. That's what I'm going to use throughout the talk. Now remember, this configuration space is a space of maps from M to N. And quantum mechanics corresponds to the case where M is equal to a point. So when I talk about dimension, so one-dimensional quantum mechanics, I'm talking about the dimension of N. In the second half of the talk, I'll talk about quantum field theory, where M isn't zero-dimensional. And so then by dimension, I'll mean the dimension of M. Okay, but for now, it's a dimension of N. So one-dimensional quantum mechanics means N is one-dimensional and M is a point. Okay, so the next ingredient is this vector space. So for each real number, let's define this formal object phi. And I make the vector space out of formal linear combinations of the phi's. So here's my formal linear combination. It's made out of these phi's, some kind of measure, and the coefficients, which are just here a function from the real complex numbers. Now, this vector space admits an action by the algebra A. The action is just diagonal in phi, and a derivative by pi. And this phi over here is what's called the Schrödinger wave function. So this is the first occurrence of the Schrödinger wave functional in the talk. So there's a one-to-one correspondence between the vectors and the Schrödinger wave functions over here. Now, the fact that there's a one-to-one correspondence means that since we have an action on the vector space, we've also got an action on the coefficients, which is again just this nice diagonal action on phi. So any questions about this quantum mechanics? Okay, now remember, the states are going to be something smaller. For one, you've got to projectivize the space to get to the space of states. So it's smaller than the vector space. And sometimes you want to impose various conditions, like maybe you want to impose that it has a fixed norm. If N is S1 instead of R, then you want to impose that it's going to be well-defined on N. So the various other conditions you impose, and at the end of all that, you projectivize. So that's how you get state space. All right, next, the Hamiltonian. So to make a theory, the last ingredient is we need to choose a particular element of the algebra called the Hamiltonian. And I'll put in some assumptions. So self-adjoint. We want the spectrum to be bounded from below, which later will actually be also a constraint on the representations that we're going to look at. And of course, it should be well-defined on N. Okay, so that's the general formalism for quantum mechanics. Any questions? So,
maybe a short question.
Yeah.
So, the operators are assumed to be acting on the vector space V, right? So, but if they just act on a vector space V, which doesn't have a norm or a topology per se, how do we define the spectrum and boundedness?
Good. So, well, the spectrum, if you can look for eigenvalues, which are, well, you'll see on the example, but we know how to act H on something because we know how to act phi on it, phi and pi. I mean, we give these definitions over here for phi and pi acting on a state. And so we can look for eigenvalues or for eigenvectors, and we can calculate their eigenvalues just because we know the action of H is made out of phi and pi.
Yeah, then you can only talk about the proper eigenvalues in the sense of linear algebra, right? And just count the eigenvalues. But then it doesn't really correspond to the boundedness of the Hamiltonian in the quantum mechanical sense, because it may have a non-discrete spectrum which goes unboundedly into minus infinity, for instance. So just counting the algebraic eigenvalues I'm just saying that it's not very similar to the standard assumptions for the Hamiltonian in quantum mechanics, right?
Oh, I don't know. I mean, if you postulate some lower bound, and then you can construct an eigenvector which beats that, then you were wrong about there being a lower bound.
Yeah, but what I'm saying that you can find in quantum, well, in quantum mechanics, you can find a Hamiltonian with purely continuous spectrum.
Sure.
And in that case, you won't find any eigenvectors. It doesn't have eigenvectors in the proper sense, that it acts with, h phi equals lambda phi. It doesn't exist because these are out of the Hilbert space, right? It's a continuous spectrum, but it still may be unbounded from below. If you define your boundedness from below purely in the sense of algebraic eigenvalues in an infinite dimensional vector space, then this is quite different from saying that the Hamiltonian as an operator is semi-bounded in the classical case for a Hilbert space, for instance.
Yeah, well, I'm going to consider a smaller space. Well, okay, so there are maybe two ways I could try to get at answering them. One of them is I can say, well, I'm going to restrict to some smaller space which does have a norm and everything nice, and then I can make sense of these things in that smaller space and then see if what I did was okay. The other one is, okay, from the beginning, I have some formal definitions, and I'm including everything I construct out of phi and pi, and if there are any eigenvectors which I can't construct, well, then I'm not counting them in the spectrum, and so I'm not going to worry about them, and I can worry about, and then I can ask if this gives me anything that makes sense or not. So the question is posed, it's just maybe it's not going to give you all the eigenvectors that you want, and so maybe I'm going to be accepting some things which are actually sick, and I'm willing, and so anyway, those are two different approaches, and the first one is kind of the standard one, and it's safer. Okay, so are there more? Okay, so let me give some examples. So the first one is where h is just pi squared over 2. Now I know how pi acts on the wave functions. I've defined that before. And so h just acts like this on a function. And so there's a set of eigenstates that looks like this. Now I haven't talked about whether I'm going to require things to be bounded or what kinds of assumptions. Of course, if I don't want things to be bounded, there are a lot more eigenstates that I can have. And there are places in physics where you want to consider those like quasi-normal modes, but I'm not going to do that in this talk. Now, if n is the real numbers, these things aren't normalizable. If it's a circle, they are normalizable, but this p is quantized. Either way, the energy is bounded from below. And that follows from the fact that I'm just considering bounded things here, which I didn't have to do. Okay. Any questions about this example? So in general, the assumptions that you want to put on these things are really problem dependent. But for a lot of problems, you're interested in this bounded eigenvectors. So use these over here. Okay, so the next example is the most important example in particle physics is the quantum harmonic oscillator. So you add this term, the phi squared. There's a change of basis with an a and a dagger. And that allows you to write h as something positive plus a scalar. And so that means you know the lowest eigenvector is just a thing where the positive operator gives you 0. So it's the kernel of A. So if you can construct anything in the kernel of A, then you found the minimal eigenvector of H. And it has this nice property over here, which means if you have an eigenvector, then you act a dagger on it and you get another eigenvector. And it turns out this gives you the whole spectrum. So here's the whole spectrum here and its eigenvalues. So what is the ground state? Well, remember, we're expanding everything out in terms of wave functions. The ground state, you said, is the thing which is annihilated by A. We know how A acts on the wave functions. And so that tells you what it is up to normalization. It's just given by this formula here. And the excited states you can get just by putting an A dagger. So that's a solution to this model. Any questions? Okay, now it's going to be useful to go on to do dimensional analysis. So to look at some different gratings which exist here. There are going to be two kinds of dimensions here, length and action. And so I define the two constants I had to have this certain number in the gratings. And that fixes h bar to have dimensions of action. And that's going to help us set us up for example 3. So in example 3, I'm going to turn on an interaction with this new parameter lambda. And the reason that this is more complicated is that now there's something which is grading 0. Now there are two different, usually you solve these problems by expansion. There are two different expansions you can consider. One is an expansion in h bar that's called a semi-classical expansion. and another is an expansion in lambda. That's called a perturbative expansion. Now, because this is the only dimensionless quantity around, the only thing at level 0 in the grading, any quantity you might want to compute is fixed by the grading up to some function, which is level 0 in the grading. So anything you might want to compute, you can boils down to just finding this function f. And so these two expansions here, the h bar expansion and the lambda expansion, are really just power series in f. They're exactly the same series. And so the perturbative expansion and the semi-classical expansion are completely equivalent. They're just power series in f. And so we can take whichever one we want. And so we fix h bar equal to 1 because there's no extra information coming from this expansion in h bar. And we just expand in lambda. Okay, so let me try to do that to solve the model. So remember, we've got a graded algebra, so we can grade our Hamiltonian. So here it is, graded. And let's just try grading the vector space too and seeing what happens. Then our eigenvalue equation that we're trying to solve is just a recursion relation. The first step in the recursion relation is just for this part, the 0 grading part of the Hamiltonian, and that was example 2. So we already solved the first step in the recursion relation. And to go to further steps, you just need to invert this thing over here. Well, this has got a kernel. The kernel is 0, but we can get rid of the kernel by fixing the EJs. So by fixing the EJs, you get rid of the kernel and you can just invert each step and you can solve it. So this model is solved. So any question about the solution? Okay, so that was easy. Let's go up to the next case. Let me just change the sign of this m squared over here. So we have what is described by this kind of potential, because you've got a minus phi squared and you've got a plus phi. So let's try to do the same thing again. We can turn it into a recursion relation. The first step in the recursion relation comes from the spectrum of H0. H0 now is this operator. The problem is this operator's spectrum isn't bounded from below anymore because of this minus sign. It ruins everything. And so the beginning of the series isn't well defined. And so we can't solve it like we solved the one before. And the reason is we're expanding about a maximum, not a minimum. So you're expanding about this point, you should really expand about 1 to the minimum. So that's not a big problem. There are 2 minima, a minimum here and a minimum here. So we can just start our perturbation theory about either of those minima. So we can just expand H in using the grading, expanding about these two minima, and that gives us 2 different perturbative approaches to try to find eigenvectors for H. These 2 different approaches that will give us 2 different answers. And at each order, these 2 different answers will have the same energy. So it gives us 2 different eigenvectors of H, order by order, which have the same eigenvalue. So the conclusion of this perturbation theory is that this spectrum is degenerate. It's a degenerate vacuum. Now so we were trying to find expansions. Each one, at each order, you get the same energy. And so perturbation theory tells us 2 degenerate vacua. On the other hand, there's a theorem which tells us the vacua are non-degenerate. So perturbation theory is wrong here. So any questions about how this argument failed? So perturbation theory told us order by order, we should have had 2 different vacua. One which starts in the perturbation theory about the left minimum, and one that starts in the perturbation theory about the right minimum. But we've got this theorem here, which tells us that all of the eigenvectors are non-degenerate. And this theorem is easy to prove. So you just consider this combination here, it's 0 by the eigenvalue equation. So you can consider 2 linear combinations of these A's, and it tells you that since A is 0, the derivative of this thing is 0. And at phi equals infinity, this is 0. And so this must be 0 for every phi because the derivative is 0. And that turns out to be this equation over here, which tells you that the 2 eigenvectors, psi1 and psi2, are proportional. So any 2 eigenvectors with the same eigenvalue are proportional. And so that tells you that the eigenvectors are non-degenerate. So perturbation theory gave us the wrong answer. Now, any question about the fact that we got the wrong answer?
So I remember we had a very sorry to interrupt. We had a similar discussion with Jarah at some point. I don't know if he remembers. And he said that this wasn't a very rigorous argumentation. I mean, I know this is very vague, but if Jarah remembers, maybe he can comment about this. If not, then maybe I'm confusing something.
I don't know. Well, in this case, you can just work out the eigenvectors numerically, and you can see that there really aren't 2 non-degenerate eigenvectors.
For me,
So
it's a little bit fast,
right
so I can't really follow carefully and say anything right now. But yeah, so let's just proceed, and maybe we can discuss it afterwards when we can look through it more slowly.
Sure.
Okay, but I mean, if the numerics shows that it's non-degenerate, then of course my question is fully answered.
Okay. This theorem, though, is due to the thesis by one of Feynman's students in the 1950s. And he claimed in the thesis that it was well known, but it never really been proved before. And so, if you want, I can dig up this reference somewhere. It's in an appendix. Okay. So what's the problem here? Well, we calculated the two vacuum using a series. I was the degree, so it's a thing which tells you the order you're at. And you have this plus or minus, which tell you that you're at the minimum on the left or the minimum on the right. And each of these things falls off exponentially when you get far away from the minimum where you start. And so does this thing. So at each step in the perturbation theory, you're localized about one minimum. The problem is, and so basically you're block diagonalizing H around the two minimum. That's what this perturbation theory is doing for you. The problem is H really isn't block diagonal. There's a block off diagonal piece, which is proportional to some number C, which is maybe small. If lambda is small, it goes off like this thing over here, x of minus something over lambda, but it's not zero. And so you can't block diagonalize H. So intuitively, we're starting the perturbation theory with this. This is the 0th order term in the perturbation series. And this is a terrible approximation because really, you know what happens if you just try starting here and integrating is as soon as you get into the other basin, the function will start getting bigger or getting, at least its norm will start getting bigger. It won't go down to zero. So this first approximation in the series is actually quite terrible. A better approximation would be an even or an odd function. And if you try starting with an even or an odd function, you find that there's actually this splitting, which is proportional to C, this thing which had an e to the minus something over lambda. And so the right answer, if you did this all out to all orders, is actually that the vacuum is non-degenerate, and there's a splitting, which is C. And we didn't see it using our power series approach because this C has an essential singularity at lambda equals 0. So that's why we don't see it in the power series. You don't see it at all in the grading. So another way to say it is our algebra was graded. We know that because we defined it in terms of H bar as one of our generators. But the vector space isn't graded. And in perturbation theory, we just looked at the graded subspace of the vector space. But this graded subspace is actually a proper subspace, and it doesn't contain the vacuum. So that's why we ran into trouble. So any questions about this point? Okay, so how could we try to do this more systematically? Well, systematically, the idea is you start at one minimum and you want to kind of integrate over to the other minimum. And so you need some kind of homotopy going from this vacuum to this vacuum. And those homotopies in physics are called instantons. It's a path from one minimum in the classical configuration space to another minimum. And these instantons always give you off-diagonal mixings, which go like e to the minus something over h bar. So this is a generic story, which is going to be important later. So there are going to be homotopies between these different minimum, and they're always going to give you these effects, which you can't see in the graded subspace of the vector space. Okay, so that's all I'm going to say about quantum mechanics. Any questions about quantum mechanics before I go on to quantum field theory? Okay, so let's go to quantum field theory. So I'm going to consider a single real scalar field. I'm going to do what's called the Schrödinger picture, in case you're, anyway, I'm going to define it now. So you've got some finite dimensional manifold M called the physical space. At each point in this finite dimensional manifold, this is space, not space-time physics. At each point x, you define two operators, phi of x and pi of x. So these replace the single operator. So in quantum mechanics, you had a single operator, phi and pi. Here, you've got an infinite number of operators, one for every point x, two for every point x. And they satisfy, again, this canonical commutation relation. So our algebra is going to be generated by this thing. And again, h bar is in the center. Now I'm going to fix M to be R, but a lot of things I'm going to say you can generalize. So any questions about the algebra? So again, it's a graded algebra with a gradient given by this H bar. Now let's consider some bases of functions that are going to be important. Usually I'm going to have in mind eigenvectors of a Sturm-Liouville system. So I'm going to want them to satisfy some sort of completeness relation. So there can be some continuous functions, some discrete functions. So the discrete functions are normalized like this, continuous functions like that. And you sum them all together to get the completeness. And for each element of the basis, I'm going to associate some number, this omega. Now, given any such...
Sorry, with respect to what inner product are you defining this M? Just
okay. Inner product on M. Well, I mean, I have a measure on M, but I don't have an inner product here. No, I mean, this star is just complex conjugation.
Okay, so it's just simple L2 on R in this case, right?
Well, I'm not going to demand that these things are normalizable, so they could be plane waves or something, but yeah, it's...
Yeah, all right. I mean, the inner product is the L2 one.
Yeah. Well, yeah, this one, and then, yeah. Okay, so given any such decomposition, given any such basis, we can decompose our fields, phi of x and pi of x, so these operators. So, I don't know why, hold on, screen disappeared. Let's give big screen again. Okay, so remember we had this number omega, which came with each basis element. So we can separate phi and pi into the part where the omega was 0 and the part where where the omega isn't 0. Let's say omega is 0 only once. So the part where omega is 0 we'll call phi 0 and pi 0. And the other parts will decompose into things called b dagger and b using these decompositions. So this is just another basis for the algebra. So the algebra was defined in terms of a basis phi x and pi x. Now I've got a new basis, which is phi 0, pi 0, b dagger, and b, where this has an index k. And this integral is really an integral over all the continuous values plus a sum over all the discrete ones. And because of the completeness relation, I can invert this. And so I can find the commutation relations satisfied by the new basis. And here they are. So the commutation relations here are just a copy of what we saw before in quantum mechanics. And the other ones are continuous and discrete Heisenberg algebras. So for any basis of functions, I've got a new basis of the operator algebra. So any questions about that? Okay, so the simplest example is just if G are these plane waves, and then the decomposition is just the one that everybody likes, giving you a Heisenberg algebra. So these A and A dagger are another basis of the same algebra spanned by phi and pi. Okay, so now for the black magic, trying to construct a vector space. So let's see some space of maps going from M to R, and for each element define a formal vector. Now, let's pretend that we could define a measure on the space. Then I could take a formal linear combination just defined like this. So we have these formal objects phi, which correspond to the maps, and I'm taking a formal linear combination of maps. And the coefficients are the Schrödinger wave functionals. So these are the things that talks are about the Schrödinger wave functionals. So for every function phi, it gives you a complex number. And if you could pretend you could sum these all together, that would give you a general element of some giant vector space. Okay, now this vector space has an A action on it. So it's just like in quantum mechanics, it's diagonal in the phi. So phi acting on it gives you this phi eigenvalue, and pi acting on it, it just acts by derivatives. And again, because there's a one-to-one correspondence between the Schrödinger wave functionals and the vectors, you could turn this into an action of phi and pi on of your algebra A on the wave functionals. So any questions about this huge, marginally ill-defined vector space and its A action? Okay, so the rest of the talk I'll talk about examples here and the relevant Schrödinger wave functionals. I'm just going to do the same examples I did in quantum mechanics, but example 1 is a little bit sick, and anyway, it's a special case of example 2. So I'll start with example 2. So let's start with this Hamiltonian, which looks like the quantum harmonic oscillator. But now remember, you've got
but example 1 was free particle, right?
yeah, but it's the
So-
case m equals 0 of this one. So if you want, you can always just take m equals 0 and try to get back to example 1 and see why it was sick.
But how is M? I thought it would be so free particle would correspond to massless field. I didn't get it.
Yeah, that's the claim. So I'm just taking the old action I had, old Hamiltonian I had for a free particle. Now everything depends on x, and I'm just integrating over x. And here's what I get: the massless field Hamiltonian. So my claim is
Here
that the
you
massless
also have this derivative, right? Which
well, massive field. Here, yeah, right, good. So I have one extra term which I'm putting in, which didn't have an analog before because there was no x argument.
So we are in 2 dimensions now.
I'm in 1 + 1 dimensions, yeah. But, I mean, there's really no time in this story, but
Naively, I would think that like the harmonic oscillator contained. Sorry, I'm just confused. I thought that mass is not related to the difference between free or so harmonic oscillator is not a free particle in a sense. Right?
yeah. So what do you mean by free is different in quantum field theory and in quantum mechanics, because of and the really difference is the interpretation of first versus second quantization. Interpretation is different. But if I forget about that and I just write down what the Hamiltonian is, then this is the Hamiltonian which corresponds to the quantum harmonic oscillator. Now we interpret it differently because we're thinking about this as a second quantized theory. But if you thought about it as a first quantized theory, then you would have the same interpretation. All right, so we're thinking about phi as something which creates particles here, whereas in quantum mechanics we thought about phi as something which excites the one particle which is always there. So your physical interpretation of these operators is different. And that's just because in quantum field theory, we like to think about second quantization, whereas in quantum mechanics, we like to think about first quantization. But if you're just thinking about operators and Hilbert space and things, there's no difference at all. I mean, this is the Hamiltonian you get just by taking that one and putting in a dx, and you put this term in, which you need for Lorentz invariance.
But it's interesting that in condensed matter, like, I mean, this dx by x kind of corresponds to the interaction between like these oscillators. I mean, if at each point of space you would imagine that having a lot of oscillators, no, this dx by x would correspond to like their linear coupling. But you say that
exactly.
This appears as a consequence of Lorentz invariance here, which kind of
here it appears as a consequence of Lorentz invariance. Of course, in condensed matter physics, you get it. I mean, there's a c squared here, which I haven't written down. In a condensed matter, you get a v squared here, and not a c squared. So it doesn't happen because of Lorentz invariance. And usually in condensed matter, you also have some higher derivative terms with their own coefficients. In particle physics, it's imposed on you by Lorentz invariance. In condensed matter, it's just something which happens because of the renormalization group flow. So that's an allowed coupling, and so it's there. And it's usually allowed by the symmetries.
Jarah, if I may ask you to maybe repeat again what you said about the particle being free is different for the quantum mechanical and the quantum field theory cases. Could you repeat that for me, please?
Yeah. So in quantum field theory, we call this well, free always means no interaction.
Right.
In quantum field theory, we call this thing free because an interaction would be a phi cubed term or higher. Interactions are polynomial terms there because they create additional particles. They're the interactions. In quantum mechanics, you call a particle free if it can't escape. So here, this thing escapes. It can't escape because you have it at potential, which goes to infinity far away. Any finite energy state is confined. So this thing isn't free. So yeah, that's the difference between what you mean by free in quantum mechanics and quantum field theory. Does that answer your question?
I see. So you're saying even if, okay, I see. Because I would expect the non-free case, as I think Karpet said, where the second term is 0, right? The derivative is 0. That's what I would expect. But you're saying even, but you're saying this would be free even with that term, right?
Yeah, in quantum field theory, this is the massive free scalar theory in quantum field theory. And the reason it's free is that there's no interaction.
Right. I guess we're regarding the derivative part as Karen said, as a self-interaction, right, between different parts.
Well, the derivative part's just part of the propagator, so there's still no vertex in this theory.
Well, I think the maybe very crude intuition here is that even if you have a bunch of oscillators, you can always think, I mean, properly changing the basis, you can just think of them as a bunch of independent oscillators with just the redefined coordinates. So that's maybe why one would still call this linear theory free theory. While if you have nonlinearities, you cannot do that. I think like that would be the intuition.
I see. Yeah, I guess I'm using the old intuition that this can be regarded as like a 1D series of harmonic oscillators, basically, as you said. Yeah.
Right, but the harmonic oscillator you call free in quantum field theory, but in quantum mechanics, you don't call it free. I mean, it's not a free particle, it's a trapped particle.
Yeah, exactly. I understand. Yeah.
Okay, so here's the massive free scalar theory. You can get the massless theory if you put m equals 0. Again, we can do a dimensional analysis, and it goes kind of similarly. And remember, we had a different basis, this A dagger and A basis, which I defined a couple slides up over here in terms of the decomposition in terms of plane waves. So this is a different basis for algebra. So one basis was phi of x and pi of x, another one was the A dagger and A's. And I could rewrite the Hamiltonian in terms of that basis, and it looks nice. It's made out of these two positive operators. Now I could write it just in terms of one positive operator like this. And if I did it, I'd get this horrible ill-defined constant term here. Now, the reason I'd want to do something like that is because writing it like this, I can see what the ground state's going to be. The ground state is going to be the thing where the positive operator gives you 0. So it's going to be the kernel of AP. On the other hand, the ground state, well, we can calculate its eigenvalue, and it's going to be this horrible infinite thing here. So the ground state isn't in the span of the finite eigenvectors. And so your minimal energy state already has infinite energy. So this theory is uninteresting in the sense that as I define states, there aren't any states. So this example is kind of sick. But it's sick for a simple reason, just because it has this one term we didn't want. So I'm going to just make another example, which is very similar to that example, just not including this term. So here's another try at example 2. I'm going to start out using this as the definition. So now all those problems are gone. I could write that in terms of the old fields at the price of introducing some notation. So I've got these colons, which are called normal ordering, and all that they mean is you put all the A daggers on the left of the A's. So this is a new example 2, which isn't sick. And again, the ground state is going to be the kernel of AP, just because this operator is positive. The kernel of AP for every P. So any questions about the new example 2? So what is the kernel of AP? Well, AP is just given by this combination, because remember, you got it by decomposing phi and pi, and that was an invertible decomposition. So let me just write inverse Fourier transforms as tildes. So then AP can be written like this. And using the commutator and the canonical commutation relations for a transform, I can write it. I can write its action on the wave functionals, and so I'm looking for the kernel of this operator over here. So I'm looking for the kernel of this, and the kernel is this infinite dimensional Gaussian over here. So this is what's called the vacuum state or the quantum harmonic oscillator. It's, as we just heard, intuitively just a product of the ground states of all the infinite number of P's. And that makes sense because the Hamiltonian is just a sum of commuting Hamiltonians, which for each cause of the eigenvectors are just products of the answers back there. Okay, so any questions about the solution? Okay, now for excited states, well, we still have the same commutation relation we had in quantum mechanics. So if you're given any eigenvector of H, you can make a new eigenvector by acting on it with an A dagger of P, but now you can do it with any P you want. And so again, you get some generalization of the Hermite polynomials. So the first excited state, for example, is this thing over here. And it is energy omega Q just because of this. Okay, so that's it for example 2. Questions about example 2? Or we go on to example 3?
Sorry, Jarah, what did tilde stand for again? The one that you have.
Tilde is just the inverse Fourier transform. So
okay, I see.
Tilde.
Yep. All right.
Okay, so example 3. So we put on the phi to the 4th term, just like we did before. Now Now, in quantum field theory, you know, there are lots of divergences, but the nice thing about working in 1+1 dimensions is that this normal ordering, which we defined as putting all 8 daggers on the left, actually gets rid of all your divergences in 1+1 dimensional scalar theories. So we're going to normal order everything and not think anymore about these short distance divergences. Now, we can do dimensional analysis again, just like we did in quantum mechanics, and we find again that there's one combination which is level 0 in the grading. And so grading fixes the answer to any question we want up to some function of this thing. And so again, that's going to tell you that the semi-classical expansion, which is an expansion in h bar, is the same thing as a perturbative expansion, which is an expansion in lambda, because you're really expanding in this quantity here. So we can set h bar to 1 and forget about it and just expand in lambda, because every h bar comes with a lambda. Okay, so anyway, this is just the same as example 3. So we can grade everything. We can write things as a recursion relation. The initial condition is example 2, which we solved. This thing again is invertible once you fix the EJs. And so example 3 is solved trivially, just like it was in quantum mechanics. Okay, so the interesting one, remember from quantum mechanics, was example 4. Now in example 4, you've got the same Hamiltonian as example 3, just with so in quantum mechanics, we remembered we had 2 ground states, and so we could expand the Hamiltonian about either one of those ground states, and that gives you a perturbative expansion where the initial condition is just example 2 about one of those 2 ground states, and then so we do our perturbative expansion about that, and that gives us, when we sum it up, 2 different states, and these 2 different states are again degenerate, just for the same reason they were degenerate in quantum mechanics. So this is the same thing we did in quantum mechanics that was wrong, but anyway, we can do it again. So any questions about our procedure here? Okay, so why was it wrong in quantum mechanics? Well, it was wrong in quantum mechanics because we started our series with 2 different states, the plus and the minus states, and we block diagonalized h effectively because everything had exponential fall off. And when we blocked and the block diagonalization of h was wrong because h wasn't black diagonal, because there was a matrix element between the 2 blocks which was non-zero. It was given by this thing over here, where this we call the instanton action, and this was non-zero. And so you had some kind of essential singularity. You didn't see it in the grading, but anyway, it was non-zero. So h wasn't black diagonal, so it was all wrong. And it all happened because of this non-zero, well, because of this instanton action over here. Now, the instanton corresponded to a homotopy between the 2 vacua. So the 2 vacua were just phi has one value and phi has another value. And there was a homotopy with a finite action, which took you from one of these to the other. Now, in quantum field theory, again, you have 2 solutions. Phi of x equals something for all x, and phi of x equals minus that for all x. But now the homotopy's got to move it. The homotopy from one vacuum to the other vacuum has to move every single point. And what that means, I'm not going to prove it for you, but what it means is that this action over here is the integral over all the different points, because you have to move the vacuum at every point of something which is independent of x. And it turns out this thing's non-zero. And so the action for our homotopy is infinite in this case. And intuitively, it makes sense that you need infinite action to move a function at all x, whereas you needed a finite action just to move a point, which wasn't a function. So in quantum field theory, this s is infinite. And that means that this c is 0, which means h really is black diagonal. So in quantum field theory, this perturbative argument works just fine. And it gets us a pretty good approximation. Well, it tells us that there are 2 degenerate vacuum states, and there are 2 degenerate vacuum states. So any questions about what didn't go wrong here in quantum field theory? So in quantum mechanics, you were ruined because you had this homotopy. But in quantum field theory, somehow this homotopy had to move a whole function at all x. And that took an infinite action. And so that homotopy is somehow not allowed. And that's what allowed quantum field theory to get out of this problem. Okay, so summing up, we have this phi to the 4 double well theory in classical physics in either 0 dimensions or 1 dimension. The 0-dimensional one, when you quantize it, gives quantum mechanics. The 1-dimensional one gives you quantum field theory. In classical physics, we had 2 solutions. There was just a number phi, and it was equal to plus or minus v. In quantum field theory, so classical field theory, you have a function is equal to either plus or minus v at all x. So again, 2 solutions. Now, quantizing This case, you get to quantum mechanics, and perturbatively it had two solutions, but actually they're mixed by the homotopy. And so there's only one minimal energy eigenstate. In quantum field theory, again, you have two solutions, but this homotopy somehow has an infinite distance. And so it doesn't do any mixing. And so each of these two solutions you get in perturbation theory is a real Hamiltonian eigenstate. Okay, so that's all that I want to say about the ground state of this theory. Any questions about the ground state? Okay, so here we had a Hamiltonian eigenstate, and we have the classical theory. Solution to the classical theory, the ground state of the classical theory, and we found it corresponded to a Hamiltonian eigenstate in the quantum field theory. And now you could ask, well, what about other solutions to the classical field theory? This theory has another time-independent solution called the kink. The kink interpolates between the two classical vacua, one on the left and one on the right. So you could ask, does this classical configuration, this solution of the classical equation of motions, also correspond to an eigenstate in the quantum theory? Well, let me ask a more general question. So let's say you had a Hamiltonian eigenstate which corresponded to some classical solution. How do we make another eigenstate? I'll call it K, which corresponds to a different solution. Now, the key to this construction is the displacement operator, this operator over here. The displacement operator is the operator which shifts phi by f, this classical solution we're trying to do. And it's compatible with normal ordering. And so the most naive guess is K, the Hamiltonian eigenstate we're looking for, is just created by this displacement operator. So this guess is nice, it has some nice properties, but it's a little too naive. It's not quite a Hamiltonian eigenstate, but it motivates this definition over here. So K is the Hamiltonian eigenstate we're looking for. This is the displacement operator. So we'll define this thing 0. So this is not quite the ground state or anything, but we'll define it to be 0. And we want to know K, but we're going to try to find 0 because it's easier than finding K. And once we know 0, well, then because df is unitary, we can get K. So why would we do that? Why do we define this new state 0? Well, we want to find K. K is a Hamiltonian eigenstate. And the key is, since K is a Hamiltonian eigenstate, we can find 0 because 0 is an eigenstate of something else called the kink Hamiltonian, which is just related by similarity transformation to the original Hamiltonian. So we're changing this harder problem to an easier problem. So we're going to find K in 2 steps. Step 1 is we find an eigenvector of this the kink Hamiltonian, H prime. And step 2 is we act df on it, and that's going to give us K. So that's the strategy. We're going to find our eigenstate in 2 steps. First find 0, then act df on it. So any question about the strategy? So we've got this new kink Hamiltonian, and it's unitarily equivalent to the old Hamiltonian, but it's going to be easier technically. So what is a kink Hamiltonian? Well, we know what, we know what df is, and so we know what h is, so we can just go ahead and calculate it. A second. And so here's what it is. It's just a number plus what's called the Pasch-Teller Hamiltonian. I'll write it down in a second, plus some interaction terms, order phi cubed and higher. Now, we remember from example 3 that interaction terms are easy to do. You deal with them in perturbation theory. It takes some work, but it's straightforward conceptually. So all the thought comes into the part which doesn't have any interactions, this Pasch-Teller piece. And this looks a lot like our example 2, except that the mass is now dependent on x. So what do we do about that? So are there any questions? Let me sum up where we are. We were trying to find eigenvectors of the Hamiltonian, but we just reduced the problem to finding eigenvectors of this Pasch-Teller Hamiltonian. And instead of having a regular mass term, which is just a number, this one's got a mass term, which is a function of x. So how do we find eigenvectors for this thing over here? Well, before solving it quantum mechanically, let's solve it classically. So classically, this is just a Sturm-Liouville system. It's got continuum modes corresponding to every real number, and it's got 2 discrete modes. One is a 0 mode, given by this formula, where f is the kink solution, and another discrete mode called the shape mode. There's a simple formula for these frequencies. So classically, the solutions are just these different GKs together with the GS and GB. So remember, every time we have a basis of functions, we can define a new basis of our operator algebra. So this decomposition, so this basis of functions, the Sturm-Liouville basis, gives us a new basis of our operator algebra over here. And we already calculated its commutators. So now we've got 3 bases of our operator algebra. One was the defining one, the phi x and the pi x. There is this new basis here. And this new basis is all very physical. Phi naught and pi naught are just the quantum mechanical operators which control the position of the center of the kink. And these B and B dagger operators, on the other hand, just create and destroy excitations of the kink. So this is a new basis of our operator algebra. So any questions about this new basis? So why would I introduce a new basis? Well, the reason is that this Pasch-Teller Hamiltonian, in terms of the new basis, is just reduced to the previous problem. So it's just the sum of the quantum mechanics example 1 and quantum mechanics example 2. So no more quantum field theory, just the sum of the examples we already solved exactly in quantum mechanics. So now everything's easy. So we know SH is a sum of positive operators, and so the ground state is just going to be the thing which is killed by all the positive operators. So the ground state is just something which is killed by pi 0, so no center of mass, and the thing which is killed by these annihilation operators. So you turn off all the oscillators. So all the oscillators are at level 0. So if you can solve these equations, then you've solved the model, at least the ground state. Then you just do the recursion, which is just cranking through. So any questions about that? So any solution to this is the Schrödinger wave functional that we want. So we can just write down the solution because the Hamiltonian was a sum of commuting Hamiltonians, which we knew. And so the ground state is just going to be the product of their eigenvectors. And here it is. This is the ground state. Where it's written in terms of these things which aren't quite Fourier transforms, but they're like Fourier transforms, but for these Sturm-Liouville kernels instead of Fourier kernels. So it's Gaussians in terms of Sturm-Liouville kernels. So this thing is the eigenvector of our kink Hamiltonian. So any questions about that? Eigenvector of the kink Hamiltonian. This is the state we called 0. Now remember, 0 isn't quite the state we're looking for. We're looking for K, the eigenvector of the Hamiltonian. And we can get to it just by acting with df. Just this displacement operator. So we do it, we act df on it, and what we find again is another Gaussian. So this is our main result, is that the first step of the recursion for the ground state of this model is just an infinite dimensional Gaussian centered on the classical solution. So it's not quite this delta function of support that you get from the embedding on my first slide, but it's the next best thing. It's a Gaussian which is centered on the delta function supported on your classical solution. So it's kind of a Gaussian about your classical solution, all defined in terms of this kind of Fourier transform, but defined for Sturm-Liouville operators. Okay, so any questions about this? Remember, this S was the discrete mode and these Ks were the continuous modes of the Sturm-Liouville system. Okay, so here's the result. Okay, so the rest of the talk, I'll make some remarks about this. So we found the first perturbative expansion. It looks like a product of Gaussians in this big infinite dimensional space, where each direction is one element of our Sturm-Liouville basis. It's centered on this wave functional supported on our classical solution. And so in this sense, you could think that this Gaussian could be deformation retracted back to the classical solution because it's just a kind of smeared out version of the classical solution in this infinite dimensional space. So you don't expect any new topology here in this wave function. It's just a smearing of your classical solution, a Gaussian smearing. So what about higher orders? Well, I spent the last year computing higher orders and there aren't really any surprises. You still get just some kind of smearing. Instead of a Gaussian, you get something like Hermite polynomials, but more complicated still because you're in the Sturm-Liouville basis. So you have an infinite dimensional, so you have an infinite number of generators. So still to any order you go, it's the same basic picture. You're in this big infinite dimensional space, but you can deformation retract back to the classical solution. Okay, so what about these instantons? Now remember, in quantum mechanics, we failed because we had some instanton which could take you from one classical solution, one ground state to the other ground state. You just have to move a point, and that had a finite action. And so it gave you a finite off-diagonal piece. Now that thing's 0 because you have an infinite action. However, these Gaussians have, in principle, infinitely long tails. The tails don't go to 0. And so while crossing from one basin, from one minimum of the potential to the other minimum, at all x would have measure 0, nonetheless, you have not measure 0 for crossing in some bounded x. So what does that mean? So let's consider this thing. This thing lives in our classical configuration space C. This you could think of as a kink, but in some finite interval, you're wandering into the other basin. So here are the two solutions, one at -1 and one at 1. You started at -1, you go to 1, but you wander a bit into the other basin for some finite amount. Now, this Schrödinger wave functional, which I defined, doesn't give you 0 on this. It would give you 0 if there was an infinite interval where you wandered into the other basin. But for a finite interval, it doesn't give you 0. And yet this thing is poorly approximated in the perturbation series because you're going into the other basin. So there's still going to be some kind of instanton correction corresponding to these effects over here. And it's still an open problem, but one I'd like to solve to try to sum these instanton corrections over here, corresponding to wandering into the other basin for some finite amount of time. And so this is already starting to explore a bit the topology of this big space. You can wander into it for these finite intervals, and you get a finite contribution. So any questions about this? So right now, all I have is a cartoon. I don't have the contribution of these things to the wave functional. But of course, these are going to make some contribution with an essential singularity to to the eigenvectors of H. Okay, so that's all I'm going to say about the phi to the 4th theory. So the rest of the talk, I'll talk about, just 3 slides. I'll talk about gauge theories. So any questions about phi to the 4th before I talk about some future directions with gauge theories, which is kind of the motivation for the whole thing.
Jarah, if I may ask, so when you're saying an instanton, are you implying like there are some quasi-particles as well? Because like that's what they do in many-body theory, right?
Yeah,
as well.
So, oh no, this.
I know you talked about the psi0
Yeah.
and pi0 operators, which probably are related to the instanton position and the momentum, right?
Yeah, yes. So there's a kind
Is
of
that what you-
quasi-particle here. Yeah, so the quasi-particle here is just taking this part of the solution over here over to over here. So if you go into Euclidean space, you have an interpolation between being here and being over here. That corresponds to the quasi-particle in this usual
I see.
Euclidean space formulation. Though it's not quite going to be a saddle point, but it'll be close to a saddle point. So in the small coupling limit, I mean, it's a saddle point up to these suppressed boundary terms.
All right.
Okay, any other questions about phi to the 4th before going on to future directions? Okay, so let me say something about the motivation for this whole project. So let me remind you what a Topf-Polyakov monopole is. So here's a classical theory where the configuration space consists of an SU2 bundle over R and a vector bundle, an associated vector bundle with a section. And you choose a Hamiltonian such that for finite eigenvectors, the norm of the section goes to some non-zero constant at infinity. And so these sections can be classified by maps from the S2 at the boundary of the R3 to the S2 at fixed radius on the section. So these are maps in pi2 S2. So there's an integer z which classifies these sections. And each section also at infinity, since it's non-zero, leaves invariant a U1 subbundle of the SU2 bundle, which has a Chern class. So that gives you another z. Now for the Hamiltonians we're interested in, for finite energy configurations, the two elements of these z's are equal. So there's really just one number z which classifies these configurations. And if they're both 1, this thing's called the Topf-Polyakov monopole. So that's the Topf-Polyakov monopole. So any questions about what it is? So it's a configuration in the space of bundles together with sections. Now there's another theory, Seiberg-Witten theory, which has a free parameter in it. And for one range of values of the free parameter, it's got small coupling, and the classical theory has Topf-Polyakov monopoles. And because the coupling's small, we can, these classical Topf-Polyakov monopoles also correspond to Hamiltonian eigenstates in the quantum theory at this small value of the parameter. Now there's another range in the parameter where this coupling is large. And there, this associated vector bundle has a section, the section goes to 0. So there is no topological charge around. So there is no classical monopole for this range of coupling. Yet there is some operator which gets an expectation value and it's causing confinement. So there's some interesting operator around. Now, the reason this is interesting is there's an interval which interpolates between these two ranges, and the operator which creates the monopole turns into the operator which causes confinement when you do the interpolation. And you can follow it through the interpolation because throughout the interpolation, it's invariant under a certain symmetry called supersymmetry. And so in that sense, this operator which causes confinement is homotopic via this interpolation to the operator which creates the monopole. So there's a monopole creation operator, something that we understand because it's really just the same topology of the classical monopole solution. And something homotopic to it is doing something very interesting, and we have no idea what it is. I mean, no idea what could be homotopic. It seems like nothing should be homotopic to it because there is no classical monopole solution here, but there still is something interesting. And the homotopy takes you to something, even when there's no classical solution. So there's no tubular neighborhood of a classical solution because there's no classical solution. There's something homotopic to it is still doing something very interesting. It's condensing and causing confinement. And so the big question for me is, what is this homotopy? What is the operator that you get to? So this is something which is really living off the tubular neighborhood, something completely unrelated to the topology of the classical theory, but probably something very simple. I don't know. So saying this again, at weak coupling, the configuration space that you're probing is just this tubular neighborhood of the classical configuration space, and it has a Toff-Polyakov monopole. Yet something beyond the tubular neighborhood in this quantum configuration space, where there's no Toff-Polyakov monopole at all, there's no embedding, there's no classical solution, is doing something interesting, and they're related by a homotopy. And the homotopy can, if you work hard enough, it can be calculated because it's invariant under this very big symmetry group, and so it's unique. And so something interesting is going on in the topology of this big space, and it's, I think, something very simple. I mean, once you say it, once you know what it is, you can say what it is in a few sentences. But right now, nobody has any idea what the monopole is turning into with strong coupling. But if you know, maybe that would let you know what a monopole is in QCD, which is a big open problem. Okay, so anyway, that's all speculation. So let me sum up the talk. So the configurations in the classical theory correspond to some big set C. Configurations in the quantum theory are some projectivization of a subset of maps from C to the complex numbers. Perturbation theory just probes a tubular neighborhood of the embedding of C in this space. But the topology of the larger space seems to be important, at least in super QCD, maybe in ordinary QCD for the confinement problem. But in order to be able to attack these, we need to be able to define these spaces and then try to understand its topology and see what this thing actually is. Okay, thanks.
Okay. Thanks, Jarah, for the talk. Any questions?
So again, a peripheral, perhaps a question to the main point of the talk. I'm a bit confused by your interpretation of the term homotopy. So the way I understand it, homotopy is that you have a curve in a topological space, well, two curves, and then a homotopy between two curves is just a continuous transformation from one to another. But the way you use the term homotopy here makes me think it's something a little bit more sophisticated.
So C is a map, and each element of C is a map from here, from M to N, and the homotopy is just a homotopy between these two maps. So the classical ground states each correspond to maps, and so you have to look at homotopy between these two maps.
So you can't homotopically say map to such phi if they are not related just by a coordinate transformation, right? Because, well, for instance, if you take just a really functionally very different map, phi prime,
yeah,
odds are you are not gonna find any kind of homotopy from between these two maps M to N, so that phi is transformed to phi prime. So this is pretty much like asking whether or not two functions on a manifold are related by a coordinate transformation.
Well,
right?
So for each homotopy, I'm also associating this number, the action. And so for one, of course, the homotopy has to exist, which is what you're talking about. But also, if the action is infinite, then I'm not interested in this homotopy either. So there's a little more information. So each homotopy as a number, and I'm interested in these finite action homotopies.
Yeah, I was basically curious how far or how close is the action by such homotopies to being transitive on the space of all such maps phi.
Yeah, this is a really theory dependent thing. So of course in Yang-Mills, I think that it's not close at all. In something like phi to the fourth, I think you can get them all. Yeah, so it's likely to be transitive if you forget about the action condition. So it's theory dependent. But I mean, that question is also relevant in physics. I mean, these are called super selection sectors in physics. So you're always trying to figure out which things are in the same super selection sector.
Okay. If there are no other questions, I have a question. So maybe it might sound a bit naive. So the ultimate goal is to understand confinement in Yang-Mills or QCD?
Yeah. So people, I mean, Toft and Mandelstam said confinement should somehow be caused by monopoles, but of course there is no classical solution corresponding to the monopole. And even if there were a classical solution, you wouldn't trust it because the theory is strongly coupled. So there's no relation between classical and quantum solutions. So my claim is that it doesn't matter that there's no classical solution. What you're really looking for is a quantum state, which corresponds to a monopole. And so the first step should be to try to find that quantum state and the operator which creates it, and then try to see why that operator condenses. So the state should have a tachyonic mass. It should condense just like in the Higgs mechanism, right? It should. And so, yeah, so that's the key, to be able to produce a monopole in QCD, not using the standard topology of QCD, because we know there's no monopole there, but using the topology of this bigger space, because that's really where it has to live. That's the space which the quantum theory sees.
Is there any possibility that one could reformulate QCD, for example, in some manner that's duality symmetric, and then there the issue with monopole will be resolved automatically?
Yeah, so that's exactly, that's a strategy. That's why I talk about Seiberg-Witten theory. So in QCD, it's a conjecture, this whole monopole condensing thing. But in n equals 2 broken n equals 1, it's known. That's actually what happens. There's a monopole. Well, there's something which is related to a monopole by this transformation. We should just call it a monopole because it's homotopic to a monopole, but it's something which is homotopic to a monopole in a theory with no classical monopole, but a deformation to a classical monopole. That thing which is deformable to the classical monopole condenses and causes confinement. So it's known there that it works. And it works in a regime where there is no classical monopole solution. And so nobody knows what this thing is, which is actually condensing and causing confinement there. In principle, you can find it because this homotopy is unique because it's the only thing which preserves the supersymmetry and is related. I mean, it's homotopic to the known monopole state, and you know that the deformation preserves supersymmetry. So it's unique. It's just a calculation which nobody's done. So I want to do that calculation and find out what this quantum state is, which corresponds to the monopole, which is condensing in a theory with no monopole. And if I find it there, then hopefully it can be found in QCD, because QCD is very similar to n equals 2 broken n equals 1.
So even there, I mean, in the Seiberg-Witten theory, it doesn't have classical monopole, so it's still some sort of formulation of a theory that
yeah, exactly. It has no classical monopole, but it has a parameter. And when you change the parameter, then there's a value of the parameter where there is a classical monopole, but no confinement. And there's another value where there's no classical monopole, but there is confinement. But you can follow the operator, which is confining, and it's the monopole operator, which does the confinement. I mean, it's the homotopy of the monopole operator. So in that sense, everybody says it's monopole condensation, even though there's no monopole. But the thing is, everybody, I mean, it's treated as understood because you can do the calculation using supersymmetry. You can figure out how big the condensate is, but nobody knows what the operator is. And if you don't know what the operator is, you're never going to be able to find it in QCD, because in QCD, you haven't got the supersymmetry magic around. So I want to figure out what the operator is. I mean, I'd guess like the regular Toff-Polyakov manifold, it's just something to do with topology, which is keeping it there. But it's going to be the topology of this quantum space, because the classical space hasn't got the topology you need. The sections go to 0, so there's no conserved charge. So it's a project which, I mean, if you're strong enough, you can do it. I mean, since you have a parameter and you know the symmetry, so you know the operator at one end, so you can interpolate preserving the symmetry. I mean, you know, it's kind of a well-defined. That's why I'm trying to warm up doing these Federer the fourth theories, so I get all the technical things down which I need.
Okay. So if there are no further questions, maybe I close the official part and then we continue.
Maybe I have a small question before you close, if you don't mind. So here you say that the curly C is the space of, well, say, continuous maps from between two topological manifolds. And then you say for the Young-Mills theory, C is the space of principal G bundles over M. So the way I understand the principal G bundle, well, usually you define a bundle over a base manifold as a continuous projection from the total space to M. But in the original definition of C, the phi goes the other way around, from M to somewhere. So how do you interpret a principal G bundle as a map from the base manifold to another manifold?
Yeah, so that doesn't, so if you look at QCD, then you see both structures together. So there you see the section. It's these sections in QCD which go to the maps, not the bundles. In physics, these are two kinds of particles. I mean, the bundles are describing spin 1 particles and the sections are spin 0 particles. And if you have the section of a vector bundle, if the vector bundle is trivial, that's just giving you a map.
Yeah, but then it means the Young-Mills kind of C doesn't fit the general pattern, or what?
No. So, oh no, it's appearing again. So when I say scalar quantum field theory, this is a subset of the quantum field theories. This is just quantum field theories which only involve scalar particles. It's not the most general quantum field theory. So
then, in general, it's going to be what?
Well, in general, they're going to be bundles and associated vector bundles and sections. And some spinor bundles too. I mean, if you.
I'm having problems understanding how a space of bundles then, as a particular case, reduces to a space of sections.
No. These are different things. So for each spin 1 particle, you have a principal bundle. For each spin 0 particle, you have an associated vector bundle with a section. The sections reduce to the maps. Those are both spin 0, just by taking the bundle to be trivial. So
there is no pattern that fits both.
These are different particles. I mean, the bundles are coming from the spin 1 and the maps are coming from the spin 0. So there's no limit in which spin 1 becomes spin 0.
Yeah. So I thought there is a general pattern so that all kinds of spin statistics fits inside and then they sort of subdiverge into two classes.
The general pattern is principal bundles together with sections of vector bundles, but that's as general as, yeah. And then if you want to put in gravity, I mean, of course, it's even worse than that. You have to then vary the different M's. But the general pattern is spin by spin.
Yeah.
But at spin 1/2, it's kind of the same story. It's just you have to allow the bundles to be tensored with spin bundles. No, I haven't considered spin 1/2 here. At spin 3/2 already, I mean, it's going to be harder to put it in this framework. And okay, well, Karapet is even higher spins than this, so.
Yeah, sometimes I wonder whether it makes sense to study field theory without gravity or higher spins and expect to find all the answers. But okay, that's.
Oh, I wonder the other way around. I mean, I think that I run into so many things here, and I wonder how it is that you can already start thinking about spin 1.5 or 2 if before spin 1 is understood. And okay, now I'm working on spin 0 really because I can't understand spin 1 until I've understood spin 0, which is this part over here.
Yeah, and it's a matter of taste. In principle, it could be that some answers come from the other side, or
Yeah, no, this is why we have more than one physicist, because in principle you expect some backwards feedback and
yeah. Okay, so we close the official part and then continue chatting on questions that are more away from the main point of the talk. Thanks, Jarah.
no, thank you.